Hi, I'm Boxed-roc and I build low watt tube amps like this one. Today I'm going to get you all started on putting one together. The power tube I use for this build is a NOS Tesla 6AQ5. It's a nice tube, nice tone. I've got the data sheet for it. It tells me things like voltages, current draw, load resistance. Tells me at 180 volts, a tube amp with this power tube will give about 2 watts output power. I've got a 12 volt transformer here. This is what I use to power the amps. And let's get started and put
this is the transformer that will be used to power the amp. It has 240 volt primary taps, 12 volt secondary taps, and supplies just over 12 volts. The MT2086 toroidal transformer has 240 volt primary taps and two 15 volt secondary taps. Connecting the secondary taps in parallel and applying 240 volts to the primary taps will induce 15 volts on the secondary taps. The voltage induced at the secondary taps is determined by the input voltage and the turns ratio. With 240 volts on the primary taps and 15 volts on the secondary taps, the turns ratio is 240 divided by 15, which equals 16, 16 to 1. If 16 volts was applied to the primary taps, 1 volt would be induced on the secondary taps. The turns ratio can also be reversed. Applying 1 volt on the secondary taps, now the primaries, will induce 16 volts on the primary taps, now the secondaries. With the E-core transformer, we are applying just over 12 volts to the 15 volt taps of the toroidal. 12 volts times the turns ratio of 16 equals 192 volts. Should we see 192 volts at the toroidal transformer output? No transformer is 100% efficient. There will be losses. An average transformer will be 90 to 95% efficient. 192 volts times 0.92 equals 176 volts. A full-wave bridge rectifier uses 4 individual rectifying diodes connected in a closed loop to turn AC into pulsating DC. 176 volts AC is 176 volts RMS. RMS voltage stands for root mean square and is 70% of the peak voltage. The peak voltage is 1.4 times RMS voltage. An electrolytic capacitor smooths the output of the rectifier and holds the voltage close to the peak voltage. Switch the power off and the resistor will bleed the charge from the capacitor. Mount all the hardware, tube sockets, transformers, jacks, etc. It may be easier to mount the tag strips that hold the filter caps before the toroidal is mounted. Electrolytic capacitors come in different capacities and voltage ratings, as well as axial and radial configurations. For better filtering and bass response, I like to use 100 UF for the first filter cap. Usually I use 100 UF 250 volt rated axial cap, but for Liquid SS Stage 3, a shorter radial cap is used to make room for the extra preamp tube, and for Freebird, a higher voltage rated radial cap is used. The negative lead on the radial capacitor is shorter and marked with a line down the side of the capacitor. This lead is connected to the lug on the tag strip that is bolted to the chassis. A black insulating disc covers the positive end of the axial capacitor. The positive leads are connected to the other lugs on the tag strip. Soldering is easy when the parts and soldering tip are clean and tinned. The NOS tag strips are dirty, so sandpaper is used to clean them, then flux, and then they are tinned. The AC leads on the rectifier are marked with a backward S. These leads are connected to the 2 lugs that are side by side on the tag strip. The negative lead is connected to the lug that is bolted to the chassis, and the positive lead is connected to the last lug. Copper alligator clips are used to draw heat from the soldering iron away from sensitive parts. Light bulbs and heaters are made of a thin section of tungsten wire called a filament. The tungsten filament has electrical resistance, and as a resistor it develops a voltage drop. Connected in parallel on the left side is 2 light bulbs and a 42 ohm resistor. Connected in parallel on the right side is 3 light bulbs. When circuit elements are connected in parallel, the voltage across each circuit element is equal. The 2 sides are connected in series with 12.5 volts across the circuit and a multimeter measuring the voltage drop across each side. When circuit elements are connected in series, the current is equal in all circuit elements. A 12AX7 and these light bulbs will draw 150 milliamps at 6.3 volts. 6.3 volts divided by 0.15 amps equals 42 ohms. When heated, the resistance of a 12AX7 heater filament or these light bulbs is around 42 ohms. On the left side, only the 42 ohm resistor is conducting. On the right side, only 1 light bulb is conducting. With near equal resistance on each side, there is near equal voltage drop on each side. With all light bulbs conducting, there is a bigger load and current draw, dropping the supply voltage to 12.2 volts. Still, with near equal resistance on each side, there is near equal voltage drop on each side. The approximate resistance on each side is 42 ohms, divided by 3 equals 14 ohms. The measured current draw is 465 milliamps. 6.1 volts divided by 0.465 amps equals 13.12 ohms. So the actual resistance on each side is closer to 13 ohms. On the right side, with 2 light bulbs conducting, the resistance is 42 ohms divided by 2 equals 21 ohms. On the left side, the resistance is 13 ohms. With a larger resistance on the right side, there is a larger voltage drop. The measured current draw is 360 milliamps. 7.9 volts divided by 0.36 amps equals 22 ohms. So the actual resistance on the right side is 22 ohms, and on the left side, 4.1 volts divided by 0.36 amps equals 11.5 ohms. Each light bulb on the right side is drawing 180 milliamps at 7.9 volts. Each bulb on the left side is drawing 120 milliamps at 4.1 volts. A 12AX7 heater filament and these light bulbs operate properly, drawing 150 milliamps at 6.3 volts. Side effects from running them outside of correct voltages range from inefficient to detrimental. A 6AQ5 heater filament operates properly, drawing 450 milliamps at 6.3 volts. 2 12AX7 heater filaments and a light bulb in parallel will also draw 450 milliamps at 6.3 volts. So I'll connect these 2 elements in series in this amp and be able to power it with 12.6 volts. It's very difficult to connect more than 1 wire to either the power jack or a toggle switch, so they are connected together in series and then to the 2 insulated lugs of a tag strip. Then any toroidal taps or heaters and LEDs can easily be supplied 12 volts from these 2 lugs on the tag strip. The grounded lug on this tag strip is connected to the ground from the other 2 tag strips, the output jack ground, and the negative leads from the filter caps. The output from the toroidal is connected to the 2 insulated lugs that are side by side on the tag strip. The positive output from the rectifier is connected across a dropper resistor to the first node on the voltage supply rail. A bleeder resistor is connected between the first node and ground. The red wire from the output transformer is connected to the first node. The blue wire from the output transformer is connected to the power tube plate, and the secondary taps are connected to the output jack. The power tube screen grid is connected to the second node. The 12AX7 heaters are wired in parallel with the light socket and in series with the 6AQ5. The heaters are pins 3 and 4 on the 6AQ5 socket. The cathode is connected by the cathode resistor to ground. The control grid is connected by the grid link resistor to ground and provides a 0 volt reference to the grid for biasing. With no tubes in, there's no load on the circuit. The multimeter common is connected to ground, so any measurements taken will be relative to this point. Plug in the power, and just like the earlier test, you can see around 244 volts at the rectifier output. The tubes are in, and there's an 8 ohm load on the output to protect the output transformer. The multimeter common is connected to one of the 12 volt supply nodes, so any measurements taken will be relative to this point. Plug in the power, and you can see 0 volts here. With heater pin 4 directly connected here, we will also see 0 volts at pin 4. Across the heater filament to pin 3, we can see just over 6.3 volts. Pin 3 on the 6AQ5 is directly connected to pin 9 on the preamp socket, so these two pins will be at the same voltage potential. Then across the preamp heaters, there's 12.3 volts, a 6 volt difference in voltage potential across the preamp heaters. This is directly connected to the other 12 volt supply node, so it will be at the same voltage potential. The multimeter common is connected to the first node, so any measurements taken will be relative to this point. Plug in the power. All current supplied to the tube plates and screen grid flows from the rectifier to the first node across a 100 ohm dropper resistor. The voltage drop across this resistor is 3.48 volts. 3.48 volts divided by 100 ohms equals 0.0348 amps, or 34.8 milliamps. Only the current supplied to the screen grid and preamp tube flows across 3.3K resistor R12. The voltage drop across this resistor is 8 volts. 8 volts divided by 3,300 ohms equals 0.0024 amps, or 2.4 milliamps. With no preamp tubes connected yet, the screen alone is drawing 2.4 milliamps. The multimeter common is connected to ground, and with the tubes in, there's a load on the circuit. At the rectifier output, there's around 196 volts, so we have dropped around 48 volts with the load on the circuit. If we measure the first node, we know the voltage will be around 3.5 volts under the rectifier output voltage, and the second node voltage will be 8 volts under the first node voltage. The cathode voltage is 9.2 volts, divided by the cathode resistor value of 270 ohms, will give the cathode current of 34 milliamps. The cathode current will include both the screen current and the plate current, so if we subtract the 2.4 milliamp screen current from the cathode current, we will get the plate current of 31.6 milliamps. To find the plate dissipation, multiply the voltage drop between the plate and the cathode by the current that flows between the plate and the cathode. With the plate at 185 volts, the voltage drop is 176 volts, times 31.6 milliamps plate current equals 5.6 watts plate dissipation. The 6AQ5 datasheet gives the maximum ratings as plate voltage of 250 volts and plate dissipation at 12 watts. So this tube could be pushed much harder if you wanted to. A 12AX7 is a twin triad tube. It has two separate tubes inside one glass envelope. Each triad has 3 electrodes: the anode or plate, the cathode, and the control grid. For correct biasing, the control grid needs a 0 volt ground reference. At pin 2, this is provided through the 2 input resistors. A 33K resistor connects the input jack tip to the grid, and a 1 meg resistor connects the input jack tip to ground. The control grid at pin 7 is provided a ground reference by a yellow signal wire through the gain pot to ground. With the power on, there's 182 volts at the second node and 177 volts at the third node. The plate load resistors are connected from the voltage supply to pin 1 and 6. At the plates, there's 131 volts and 136 volts, dropping 41 to 46 volts across each 91K resistor. 45 divided by 90 equals 0.5 milliamps. The same current that flows through the plate load resistors will flow through the 2K cathode resistors. The cathode resistors are connected from pin 3 and 8 to ground. 0.05 milliamps times 2K equals 1 volt, so there'll be around 1 volt at the cathode. The AC signal comes in at the input jack to the control grid on the first triode. It's picked up at the plate and sent to a voltage divider. A capacitor is used to block the DC plate voltage, but allow the AC signal to pass. The AC signal is picked up on the center pin of the gain pot and sent to the control grid on the second triode. It's picked up at the second plate and sent to the control grid on the power tube.